Okay, guys, can you hear me?
Yeah.
Yeah. Are there any questions? We have a few minutes before we get started on the lecture.
Yeah, I have a quick question about one on the homework.
Yep.
Just about how to read, because when we I'm just trying to get used to the terminology, right? So when we say this fancy P is a binomial product measure,
Yes.
I'm thinking I'm supposed to be thinking of probability measure and thinking of it as a function from the sigma algebra to the interval 1, 0.
Yeah, I should not have written that. This we haven't really used that terminology in class. Let me just bring it up. Um, what it means is you have these coin flips, and so there'll be a probability p for the coin flip to be here. The coin flip is going to give you 1 and -1. So the random variable is xj. It's question number 1 you're talking about, right?
Yeah.
So what is meant by this binomial product measure is that xj take on these two values, 1 and -1, with probabilities p and q, and the IID. So what is the notation? X1, X2, X3, X4, and so on. They're all independent.
Okay. So one thing I was confused about was I was thinking of this sample space as like a string of heads and tails.
Yes.
Right. But the input in each of these random variables is only one head and one tail.
No, that you see there's a W here.
Oh, okay. WJ.
And there's double J here, right? So W is string, and J is the jth coordinate in that string.
I see. So the random variable, the J of the random variable determines which head or tail you're picking out of this string.
Yes. Yeah. Right. So an element inside. Let me switch over to my document.
Oh, that makes sense, because it's like the J head should be like the J random variable should.
And an element inside this head tail space. If you had this goes up to n, right? Such a thing. This is nothing else than just some big vector with W1, W2, down to Wn, with Wj being either heads or tails.
Right. Yeah.
And so
I got it.
When you're talking about a binomial product measure, it's just when I have these, so xj of omega, this is just defined to be, this was 1 if wj would be heads, and -1 if wj would be tails. So these ones here would probably have been better. These problems are the old. This would have been better for me to write them as these psi j's, because this is what we've been doing in class, right? The psi j's are the
right, and we use x as the Wolf process.
Yes, I should update this notation here, but I mean, it would have been more appropriate to call these psi's for the -1 and 1, because that's what we've been doing in this class. And at the end of the day, it's all just notation, right? Whether I write xj or psi j, it's just notation. It's just the jth coin flip.
So one thing I'm still a little unsure about is we're letting P be a probability measure, and the inputs of P are elements in the sigma algebra.
Yes. Right. So here the
So we're not
sigma algebra, this is going to be just 2 to the omega.
right. Yeah, it's gonna be an element of So what does it mean with probability of heads equal to P and probability? So what I'm getting confused about is like the string, the element in this sigma algebra that we're inputting.
So what's the
Into
probability of this thing here being 1? And this is going to be P.
that's when it's omega j is a head, so it'll be half.
No, P.
P. Oh.
Right, in the assignment, it's P and Q. So the other one is.
Okay, I see. I wasn't connecting the random variable being the.
But because this here is the set you're looking for all those omegas that has as their jth coordinate h. What's the probability of that set? Right, this here's.
Oh, I see. That's
such that omega j is equal to h.
Got it. Yes.
Okay.
Yes, that makes sense. Okay. Yeah.
Very good. All right, so I think this pushed us over the 6:40 clock. Good questions. Like it. All right, so hope we all here. Again, the midterms are coming up. So next week, I just want to make clear that next week is going to be a little bit different. Next week there'll be different office hours, and they are to be announced. Just heads up, and also so you should check the announcement for schedule of midterms. Please sign up. Sign up if you haven't. Check correctness if you have. I'm bound to make mistakes here, so check that your slot is the one that you think it is. Okay, so we have a few things to do before the midterms, and so we have tonight, and then we have 2 lectures next week. So I'm hoping I can get somebody to volunteer to test out the and try to do a sample problem in class, so you guys can see what it is I have in mind for the midterm. So if anybody is interested in doing this free of charge, by all means, let me know, and then probably on next Thursday, so a week from now, we can have some sample runs, dry runs, whatever you want to call it, so you can see how it is. And of course, this is never going to get held against you. This is just an opportunity for you to practice, so you guys can see what it is that I have in mind, given that we haven't tried this before. I should also say that I put a link up, another link in the announcement for how you can convert your camera on your phone into a document camera. This is again something that you can play with before the exam. So you can write on a piece of paper if you decide to do that. Okay, the starting point, what we're going to be doing today is going to be about radon nicotine processes. So nicotine derivative processes. And so where we are at is over here in the thin book. We're going to be looking at a section in the thin textbook that we're using. We're down here. We're going to be down here in section 3.2. These 5 pages. This is what we're going to be doing tonight. When you do this, we're going to run into a version of base rule. And you guys have seen base rule being used in probably in different courses, but at least in the probability course that you've taken. This is one of the first things that you often see. So let me just recall it here, because we're going to be looking at a much more general version of base rule in what's going to come over in this section here. So the conditional probability of A given B, like the definition of this quantity, of the definition of this probability measure is that you take the probability of the intersection and divide it by P of B. Right, so we're going to make the assumption that P of A is positive and P of B is positive. Right, so I have 2 sets. I'm working with 2 sets that have non-negative, have strictly positive probability. So that's the definition of the conditional probability, P of A given B. Right, so that's a probability measure. Fixed B, then this is a conditional probability. Okay, we talked about that. We proved that this is a probability measure. Then there's the other one when I swap them. So I can do B of A given B. And of course, this is going to be defined exactly like the other one. You just swap the roles of A and B. So now this allows us to combine. This allows us to combine. So I can express one in terms of the other. Right, so if I want to express the top one in terms of the bottom one, I can do that. So now it's not a definition anymore, right? This is a conclusion. So downstairs I'll have P of B, and upstairs I'll have P of B given A times P of A. Right, so this here is referred to as base rule. And I'm hoping that we have all seen and we all try to work with this. This here is base. This is base rule. So what I want to show you now is an example of this. It has endless applications, but one main application is this is for testing, which is perhaps more relevant now than it's been in a long time because of this COVID pandemic that we live in. So what I did was I uploaded some problems for you guys to look at. So let me just find the file. You go on Canvas somewhere, and there's just 9 pages of additional problems to look at. The first ones, the first handful or so, is about base rule. And the one I want to hone in on, the one I want to look at, is this problem number 4. Because this is perhaps relevant for what we are enduring right now. And the basic question is, like you turn on a news channel tonight, you turn on CNN, you turn on whatever your news channel is, at some point you're going to be talking about how many people in the US have been tested, how many people have tested positive, how many people have died with a positive test, and so on and so forth. So a basic question to ask is, if you test positive, what's the chance that you're actually sick? It seems like a reasonable thing to ask, right? You go down to the doctor, you get tested, he tells you it's positive. What does that tell you? Does it tell you that you're actually sick or what? So then the doctor tells you on top of that that the exam, the screening device that he's using, the test that he's giving you guys is 90% accurate. I was trying to look up numbers earlier today to see if I could find out what these COVID tests they actually give in terms of accuracy. And it ranges widely. The example here that I'm doing in this problem is 90% accuracy. So does it mean that if you test positive for COVID with a test that is 90% accurate, does it then mean that you have a 90% chance of being sick? And the answer is no. This is not what accuracy means. To figure out what this question is, you need Bayes' rule. And when you see the calculation we're going to do, if you've not tried this before, this might seem like there's something really wrong. Okay, so here's the starting point, right? We have a test that is 90% accurate, right? So if the patient is sick, it's going to give you the correct, it's going to give you a positive test 90% of the time. If the patient is healthy, it's going to give you the correct answer 90% of the time. And then we make the assumption that about 1%, in this problem here, 1% of the population suffers from the disease. Right, so these are the information that you're given in such a world, such a test situation. If you test positive, what's the chance that you're actually sick? Right, so if you just skim down my solution, you can see it's 8%. Okay, so let me show you how you get these 8%. So you want to know what is the probability that the patient is sick. Patient is sick given that the test is positive. Right, that's the goal. Can we figure out what this thing here is? Right, the test is 90% accurate. So what that means is that the test is positive. Positive test, given that you're sick, patient is sick, this is 90%, 0.9. Likewise, the probability that a negative test, given that the patient is healthy, is also 0.9. Then the probability, the unconditional probability of a patient is sick was this, was it 1%, 0.1. 0.01. So this is what you're given. The test has 90% accuracy in the sense that the probability that the test is positive, given that the patient is actually sick, is 90%. The probability that the test is negative, given that the patient is okay, is also 90%. In such a world, what is this probability of here? Yeah. Before I launch into the calculations, does this make sense to you guys? Have you seen calculations of this sort before? Have you seen stuff like this before in an earlier class?
Yes.
Okay. So it's not surprising what you're going to get out here in the end then. And so how do you attack it? Well, what always comes out here is that when you're talking about accuracy of these tests, you're always given the wrong thing. you're always given that you condition on the thing that you want here, and the positive test you want to go over here. So you want to compute exactly the opposite, right? You want to compute, if you test positive, you want to know what is the probability of you being sick. But that's not what is given to you. So to go from one to the other, you use Bayes. You use Bayes' rule, right? You use this thing that we have here, that you can get one from the other. But the key thing is this ratio here. There's a P of A divided by P of B here. That thing, by multiplying onto this factor, you can go from one to the other. So even though we have 0.9 here, so even though you would have 0.9 sitting here, this ratio, P of A divided by P of B, this can completely mess up this 0.9 if this is a small number. So let's try to calculate this. We will use Bayes' rule. So we will say the probability that we're interested in. So the probability that the patient is sick, given a positive test. You will swap it using Bayes' rule. You will write this here as the conditional probability that the test is positive, given that the patient is sick. And then the correction term, this is the probability that the patient is sick. And then you divide by the probability of a positive test. Okay, so now it's just a question of working out what these quantities here are.
Oh, is the bottom law of total probability?
Yes.
Or
so that'll be one way to get at this one. So we can get here that, right, to get this thing, we will say that the set of a positive test, right, I can write this here as positive test, and then I can intersect with the patient is sick, because either you're sick or you're okay, and then you do a union. So this is a disjoint splitting. We're going to do the union of the patient is sick, union patient is okay, I get omega. So I'll have a positive test here, intersection with patient okay. So if I have that, then I'll be able to say that, well, what I have downstairs, I should write it down here. So this is just a little comment. So then we'll have the probability positive test, given the patient is sick, times the probability that the patient is sick, and then 1. And these are disjoint, right? Because you can not both be sick and okay at the same time. So here we have the probability of an intersection. Right, so the probability of an intersection, I can do that by computing a conditional probability. Right? So I can move this thing up there and get the probability of the intersection. And I have these ones up here. So I'll do probability of intersection. This will be the probability of a positive test, given patient is sick. Times the probability that the patient is sick. And then plus, and I'll do the same thing for this one here. It'll be the probability that I have a positive test. Given that the patient is okay, times the probability that the patient is okay. And now I have probabilities for all of these. When you plug in, and if I manage to plug in correctly, you get this 8.2%. So what happens is that you take a test that is 90% accurate. Before you take the test, you have a 1% chance of being sick. Then you take a test, the test comes back positive. Now you have an 8.2% chance of being sick. This is the flow of information that we're modeling. We learn stuff over time. That means that the conditional probabilities, they might be very well be quite different than the probabilities related to the unconditional ones. So it's just something to keep in mind when you see the news and you see how many people have tested positive, and we see this every day multiple times on social media, on whatever. Just keep in mind that there's something called Bayes' rule. And for an example like this one, a 90% accurate test in a population that has a 1% infection, you testing positive, your probability is far away from 90%. It's 8.2. Other questions on this? I'm hoping you've all seen Bayes' rules. Let me just finish up with a different application of Bayes' rules. I won't do all the calculations for this one, but it's this is an old game that used to be on TV. The Monty Hall problem. Anybody heard of the Monty Hall problem?
So on the goats and the car.
No, not the one I have in mind. So there are 3 doors.
Wait, wasn't it a TV show?
It was a
And
TV
then like there's the prize behind
Yes.
one of the doors.
3 doors and 1 prize. Right. So you imagine you have your 3 doors. Door 1, door 2, door 3. And we play. So there's a prize behind one of these. And you don't know which one, of course. So the game starts with you pick one, pick it all. Pick one, so you'll have a third chance of picking the right one. Of picking the winner. Okay, so you pick one, say A. So you pick one. You have a third chance of picking the right one. And say you pick A. So then the host, he opens B. Say. And B is empty. And so here's your dilemma. Are you going to stick with A or switch to C? What do you think? Nikita wants to switch. Richard wants to switch. I agree, let's switch. Does anybody care to assign probabilities here? What do you think the probability is? The conditional probability that it opened after you see B is being empty. What do you think the probability is that, so conditional on, what is the probability that price in A, well, the unconditional one was a third. What about the probability of the price in A given that B is empty? So if you want to figure out what this is, and I see 3 switches. Okay, so if there are 3 switches, presumably this one here is going to be less than the probability that the price is in C, given that B is empty. Years ago, this was a when in particular when this game show here was going on. I don't know why the people that ran this game show, but they had not heard about baseball, so they were having a hard time with this thing. They thought that this was a good game, but of course, as you can imagine, that there is actually a straightforward thing that you need to do. You always have to switch. You can figure this out by computing these 2 probabilities. For those of you that haven't seen this before, there are versions of this being used also in screening for jobs. The easiest way that I know that I can try to convey why we might want to switch is to look at more outrageous ideas. Okay, so if you, instead of 3 doors or boxes, consider, say, 100. Right, so I'll line up my 100 boxes. And you pick one. You pick one to begin, right? So you pick this one. Box number 1, 2, 3, 4, 5. You pick 5. And of course, this is your chance of winning. So you pick number 5, and you have 1% chance of winning. Then the host, he opens 98 boxes or doors. Right, so he basically scratches out 98. So he goes, this one, this one, this one. Oop, we're gonna leave that one. This one, this one, this one, all the way, all the other ones open. So now your choice is, he leaves number 4 closed. Your choice, switch or keep. So instead of just having 3 doors, play the game, but with 100 doors, or however many doors you want, 10 doors. And just imagine the game host, he's gonna go down the aisle and he's gonna open, 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 and then, okay, we're gonna jump over this guy, open, 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 open. What does that tell you about the door that he just skipped? There's probably something in that door, right? And that's why he skipped it. It might, of course, be that you were so lucky to have picked the correct one. Small chance, but you might have picked the correct one. But it might also just be that the host who knows where the price is said this was exactly where it was. And so he skipped all the other ones except that one. And that means that this one probably has the price in it. And whereas the one that you have probably does not have the price in it. And so it'll be optimal for you to switch. Okay. This was a sidestep. This is not, these are applications, interesting applications of, I think, the interesting applications of base rule. The Monty Hall problem, you can Google it. It has a long history. There's a lot of debacle about whether or not what I have told you here is actually correct, or if I'm somehow cheating somewhere. There are endless Wikipedia sites and documents written on this. So in this day and age with, there are some people that really don't want this to be true, in particular the people that are behind this program up here. This here is a textbook example of an application of base rule. The other one about testing positive and testing negative, this is something that I think is quite important. If you have not seen anything like this, try to Google for COVID-19 and base rule. There are lots of tests that people perform, in particular when you get older into your 40s, your 50s, your 60s, and your 70s, there are all these screenings that you get. And some of these screenings, they come with real problems. So it's not like you can just, getting a COVID swab, if you do the saliva test, this is not very invasive, but you're not going to get this high accuracy on a saliva test typically. If you get a more invasive test, you get a high accuracy. But as soon as you get a more invasive test, you increase the problems that you might have because you've had a more invasive test. So then you have to balance, like, what on one hand am I willing to have a more invasive test to increase what I have here, so actually get a more precise test done, so this probability here increases. So there's a trade-off between having there's a trade-off between having a very accurate test and then how costly it is to have an accurate test performed, let alone paid for. So these are things that you, as a user of a test, you should just be aware of. What do I actually get when I perform this test? Well, I'll get a signal, but how high quality signal do I get? And what's the cost, on the other hand, of getting this highly quality signal, right? A test is not free, and free here is both in terms of money, but it's also in terms of the risk that you assume by having the test done. So this is something that I think we should all just know, and so we make better informed decisions. I'm not saying one thing you should do and one thing you should not do. All I'm saying is you should just at least know how base rules feeds into something like testing, given that everybody is getting tested for one thing or another throughout their lives. Before we move on to the next topic, I want to make sure that there are no questions about this basic form of base rule. Okay, if that's not the case, then we're gonna get back and talk about. We're gonna go back and talk about martingales and base rule in this more abstract setting. Okay. So say that. So say so we should recall the random economic derivative. Right, so this is my dq and dp. So if Q is absolutely continuous with respect to P, then there exists this random Nicolam derivative, dq dp, such that, right, this here means that P's null sets are also Q's null sets. So if you have that property, you're absolutely continuous with respect to P, then I can find a random Nicolam derivative. And what does it mean to have a random Nicolam derivative? It means that the dq dp, this is it's a measurable, so it's F measurable. It's non-negative. Right, so it goes from omega, it's non-negative. And it has this property that I can compute probabilities under Q simply by integrating with respect to P. So I can take Q of A, I can calculate this probability simply by calculating expectation with respect to P. I should call it C, this is dq to P. Right, so just a note from 3 with A being omega, we get Q of omega is just the expectation of dq and dp, right? And this was 1. So this is a non-negative random variable that has expectation 1. So that's the random Nicolam derivative. If you haven't, so the theorem is that if you have absolute continuity, I'm hoping we can all remember what this here means. This here means that P of A being 0 implies that Q of A is also 0. It's not equivalence, this is just an implication. So if I take a set that has no mass under P, it also has no mass under Q. So then to get the process, to get the Radon Nicodim derivative process, we use we define the Levy martingale. So this is my Zn, which is the conditional expectation of dq to P given Fn. So that's that guy. And we proved it in class, but let me just repeat the proof once more because we're going to be using this calculation quite a bit. So let's just recall the proof. So let's recall why this object here is a martingale. What we will do is we'll compute the conditional expectation of Zn plus 1 given Fn. And then we want to prove that this conditional expectation is going to be exactly Zn. So the way we do it is we start by just taking the definition, plugging it in. Okay, so I can do that. This here is the conditional expectation of dq dp given, well, n plus 1, so I need an n plus 1 up here, given Fn. So now I have the situation where I have the conditional expectation and then another conditional expectation. So I have these two sigma algebras sitting next to each other. So which one wins?
The smaller one?
The smaller one.
Yeah, the smaller one.
If n is inside, if n plus 1, the smallest guy wins. So I'll get here dq dp given fn. And voila, this was C. So that's one thing, right? So from here we get, so then we get a bunch of things. Then we get, if I'm starting to compute the expectation of, say, Cn plus 1, okay. This is apparently, so I can, for example, use the same property as before, like iterate the expectations tell me that I can take the expectation of a conditional expectation. If I take the expectation of a conditional expectation, I'm going to get the original expectation. So this is true. Then I can use the property I just got, namely that this is apparently the same thing as the expectation of Cn. So the expectation at a later time is equal to the expectation at an earlier time. So I can keep doing this, and I end up with Z0. But what's the expectation of Z0? Well, Z0, where was he? C0 is the expectation of dq dp. Right, so this is a 1. So the process has constant interpretation over time. Okay, that's because it's a martingale. Keep in mind, having constant expectation over time, this will give you, if you're a martingale, you will have constant expectation over time. However, to be a martingale is much finer than just having constant expectation over time. So this here is not the definition of a martingale. Okay? This here is just an implication being a martingale. So that was one. Another thing we get is, I know that the QDP was non-negative. So this will also imply that Zn being the conditional expectation of the QDP, given if n, this is also going to be non-negative. So my Radon-Nikodym derivative process, this conditional expectation here, it's a martingale. It has expectation 1, and it's not negative. What kind of examples of a Cn could I have in mind? Well, the one we have in a binomial model. So an example. So in our multi-period, in our multi-period binomial model, we will have our Zn. Our Zn will be p tilde divided by p to the power number of heads times 1 minus p tilde divided by 1 minus p to the number of tails. So I should write that down, where the number of heads, this is the number of heads in first n tosses, and this is the number of tails, is equal to the number tails in the first n tosses. So for good measure, we should probably check that this really is a martingale. What do you guys think? Does it look like a martingale?
Well, yes.
Nothing wrong with a sanity check from time to time. How do we do it? Well, sanity check on the martingale property. This is Cn plus 1 given, and then information about the first n tosses. Here comes the kids. Good night, guys. Good night. Time for the kids to go to bed. Okay. Becky. Then we'll plug in Cn plus 1 here. So that's the mess we have up here. P tilde over P times the number of heads in the first n plus 1 tosses now, times 1 minus P tilde divided by 1 minus P, number of tails in the first n plus 1 tosses, given whatever the first tosses were. So can we calculate something like this? Yeah. We use the, whenever we face a calculation of this sort, where we have something in here that involves n plus 1, something out here that involves n.
Iterate.
You always have to express whatever you have in here in terms of something that involves n, and then something that's independent. That's the structure that we have been using in this class quite a bit. So you want to start by saying, okay, let me write whatever I have in here in terms of something that is Fn measurable. Okay, how do we do that? P tilde over P, and then I should probably raise it to the power, not Hn plus 1, but to the power
the Greek letter xi or 1.
So keep in mind psi is the outcome, right? So psi, instead of going up to the outcome of the n plus 1, the first
n,
you go up to n. But of course, then I also need the equality to be true. So I'll need to correct this by the outcome of the nth toss. So here I'll have Hn plus 1 minus Hn. There's a minus sign here. Right, so this is the outcome. This is the this is equal to 1. 1 if toss n plus 1 is heads, it's equal to 0. Yes. I also have the other guy do the same thing. 1 minus P tilde over 1 minus P. Number of tails up to n times, and then 1 minus P tilde divided by 1 minus P, and then the number of tails up to Tn plus tails of the time n plus 1 minus the number of tails up to n. Right, so this quantity here, this is equal to 1 if toss n plus 1 is tails and 0 else. Okay, another condition on anything. So then, did I succeed in doing this calculation where I broke it up? I would have something that is measurable and then something that is independent. Well, if you look at what is measurable, like the first, here I'm conditioning on the outcome of all the first n tosses.
So are we trying to use the independence lemma?
Yeah. Here it's going to be a little bit simpler because you don't have a function. We just have a product. So the first component, the one with the number of heads up to time n and the number of tails up to time n, this is going to be measurable. So they can go outside. Remember when you compute the conditional expectation of a product, where one part in the product is already measurable, that thing can travel outside. And so you do that, you'll get this part here will go outside. So we have that with red. This part here, he can go out there. And this part here, he can also go out there. And what do I get when I combine them? Well, when I combine them, I get exactly Cn. Right? So the first thing I get is Cn. Now, I also have all the stuff left in here. And so how the thing that's left in here only depends upon the randomness in the thing that's left in here only depends on toss n plus 1. And how does toss n plus 1 depend upon the first n tosses?
Conditioning on it doesn't make a difference to the unconditional.
So we just compute the expectation. So we need to get our hands on the expectation, p tilde over p, of getting a toss getting a heads in the n plus 1 toss. It's almost impossible to say. 1 minus p tilde divided by 1 minus p, and then the number of tn plus 1 minus the number of tn. No conditioning anymore because you had independence. So what is this expectation? Slowly getting to the end here. What is this expectation? Well, there are two possibilities, right? Either toss number n plus 1 is heads or toss number n plus 1 is tails. So the probability of a heads is p. Okay, if there's a heads, then this thing here becomes 1. So I get p tilde over p. And this one over here is just a 1. So 1 by 1. That's okay. The other one, if I get on the other, if it's not heads, it's going to be tails. So we will have 1 minus p, and then this thing will pick up 1 minus p tilde. This will be a 1 divided by 1 minus p. You get this mess. And so when you factor out, you get p tilde plus 1 minus p tilde. You get your Cn. So this is how the Radon-Nikodym process looks like in the binomial model. So when you look at a Black-Scholes model, that'll be one of these. The one that comes up in Black-Scholes, maybe before I move on to that, are there any questions on the calculations that we've done here?
Yes, can you explain the number of heads n plus 1 minus and then the subsequent part?
Right, so this notation here, this is a random variable, and it just counts how many heads in the first n tosses. I shall have my psi one, depending on whether the first toss is heads or tails, this will go to U or it will go to D. So I could have had that So this will be the same, and then this will be the same. Right, so say that the first coin flip leads to psi1 being u. So say we have an omega that the first coin flip is u, and then the last two are just going to be d. For such an omega, the number of heads would just give you 1, right? Then h3 would be 1. Is this confusing? Does this help?
No, I'm still confused. I'm sorry.
Okay, so let's try something else. Let's try to figure out what is C1 equal to. Maybe this will help. So I'll compute P tilde of heads. I'm going to try to figure out what is C1 here. Okay, so I'm gonna perform the calculation that we have prescribed this random derivative. See, right? I get the measure on a set simply by integrating the over that set with respect to the random derivative. So what I'll do here is I'll try to figure out what is Z1. Okay, so I'll measure the probability of heads in the first toss on the P tilde. So I'll perform this calculation. But now I'm just integrating over 1 point. So this here will be my Z1 of heads times P, the probability of getting heads in the first one. Right, so on the left-hand side, I'll get P tilde. And on the right-hand side, this will be P. So I'll combine. You see as P tilde of, this is P tilde divided by P. This is equal to Z1 of heads. We good on that?
Yes.
Okay, so now we do the same thing. What should be C1 of tails? Any guesses?
1 minus P tilde over 1 minus P.
Okay, so now we move on. How about if I look at, so I'll move into something that involves, so this was my C1, right? Now I know what C1 is. So what about C2? So now I need to look at both the first and the second toss. So if I integrate over H, I get 2 heads. This will be the same as an integral over H of my C2 of dp. And this would be C2 over of H times this probability of H. So now what is the probability of getting 2 heads on the P?
P squared?
Yeah. Right, because the IID, right? So the independent of each other and the identically distributed. And what is the probability under this one? Well, this is the one we want to be P what? P tilde squared. Mm-hmm. Right, so then you get C2 of H, the random negative derivative of HH, this is going to be P tilde squared divided by P squared. But I could perform the same calculation if I did, if I wanted to have P tilde and say we mix it up, we get H and T. So then what would that be? It'll be C2 of HT times P of HT. And now what's the probabilities here? Well, the first one, this is
P tilde times 1 minus P tilde.
And this one?
P times 1 minus P.
So you can start seeing the pattern now.
Yes, I can. Thank you.
Okay. You start seeing the pattern, yeah. Okay, so what is all this stuff good for? Why would we ever care about this random Nicotin process? Well, why would we care about this thing? Well, so keep in mind this conditional expectation. This conditional expectation has two properties. Right? Should somebody ask you for your all midterm, say in a few days, what properties a conditional expectation has? It has exactly two properties. Property one, this is if n measurable. Property two, when I integrate it, right, when I integrate it, I get the same. When I integrate over set A, I get the same thing as when I integrate the random variable, the QDP, with respect to P, over those sets in the sigma algebra that we condition now. But you see, this quantity here, we go back and we use the property that we had here. That expectation, this here is the same. This is just, the first part here is just notation. Like these two things, notational wise, except for notation, this is exactly the same. But this thing here, like the random derivative, this here is my Q of A. So what it says is that, so on Fn, which of course is inside F, Q's random derivative is Fn. Oh, sorry, is Zn. So on the big one, it's the QDP. If I want to get the random derivative on a smaller one, I just condition. And so that's where the random derivative process comes in. So you will be able to prove, so a lemma, which is basically what we have here, but let me just show it to you. Find this lemma stated in the format that we need. It takes a little bit of digging, right? So we're primarily working in the thin one, the number one book. But we're going to need a result now that is in this one. And you have to dig a little bit to find it. It's not, I don't know why he put it the place he put it, but nevertheless he did. It's in here, but you have to know where to look. And the place to look for it is all the way over here on page 210. Down here is where you see these random derivatives. So now what we're going to be doing is we're going to be looking at this lemma here, lemma 521 and lemma 522. These two lemmas is what we'll probably only have time to talk about one now, but we'll talk about the other one next time. So we'll do lemma 521. So this is 521 in 3, 2. And here's what it says. It says, so let y be fn measurable and integrable. Then if I am to compute the expectation under this measure of the random variable y, so I'm computing now here under the tilde probabilities, I can calculate this expectation simply by calculating the expectation under p of y times cn. And the proof, we're going to give a simple case, and then you need to approximate with sums and limits. We'll just do it for the simple case where the random variable y has the form 1a, where a is some set fn. Okay, so how will we do it? How will we do it? We will compute the expectation. We compute the expectations, and we need to settle on, should we call it q or should we call it p tilde? So here I'm using the letter q, so I should probably keep carrying on that q instead of putting a tilde here. So let me just change this up to a q. This becomes eq, expectation under this measure that has zn as its derivative process. eq of y, this is eq of 1a. Well, this is q of a. So that was the one we had here. Then you go all the way back. Go from here all the way up. This is also the integral. This is also equal to the integral over a of cn dp. qa, go all the way up. This is this guy. What that was, the expectation of 1a zn. And then you just use that 1a, this is my y. So I have the result for indicators. Then the next step, next you write it for y being finite sum k equals 1 to n. You take some yks, you take some indicators for ak intersection with aj is empty for all k not being j. Then you assume that, so this is the next, and then next. Take limits. So we've been doing this before. I won't take you through it one more time. But what that allows you to do is to calculate expectations on the Q. You can do that if you have that the random variable in question has an fn measurability property. Then you can just multiply it in with the random derivative that is measurable, that conditional expectation up to time n. That's the one that goes in there. I think this here is where we might call it quits. Let me just alert you to these additional problems that I pulled from before. The base problem. I put up a few more here because I put up a few more. Where is it? Here. I put up a few problems about this Radon-Nikodym process. So if you want to have some more practice on this, there's a problem 10, 11, and so on. And you can see here comes the Radon-Nikodym derivative that we just talked about. So if you want to have some more practice on, what we've been talking about, well, this could be one place to get started. Are there any questions before we call it quits?
Yeah, I have just so the tildes are the risk neutral probabilities
In the binomial model, yeah.
in the and you remember the sheet with Z2 that you were talking about?
Yep. Let me bring it up.
I was wondering about because I thought that you had the integral when you have like an expectation. So I was kind of confused to see the p tilde turn into the integral.
This one here, this is the expectation of the indicator for the set H of C2.
But why is it equal to the tilde probability?
Because
That's just the definition of it. Okay, yeah.
it's just a Radon-Nikodym derivative, right?
Yeah. Sorry, I think I got it now. Yeah.
Right. This here is when I have dp tilde dp is equal to C2. That's what this equality sign here means. Like I get the p probabilities simply by integrating this random variable with respect to the p probability.
Got it. Well, now I got it. Yeah.
Okay. But whether I write so what does not have any what is all notation is whether I write it like this or I write it like that. This is tomato. There's no information here. Right? Here, this equality sign has a lot of information, but the fact that this term and that term are the same, that's just notation.
Okay, I see. And it comes from the Radon-Nikodym. This comes from the definition.
This one here is the Radon-Nikodym derivative, right? What does this symbol here mean? It means this equality there.
Okay, I see. Thanks, Professor.
Yeah, so Alice has a question too. Can I explain what EQ is again? Well, if I take on page 11. So EQ of Y, this is the expectation of a random variable under Q, right? So this here is defined as the supremum over so when Y is positive, this is defined as the supremum over expectations of say X under Q where x is below y, x is simple. And then the expectation, so if I have a simple guy, this is one of these sums we had from before, right? So this is xi times the indicator for ai. I runs from say 1 to n. ai and aj are empty whenever I is not j. Right, so if I compute the expectation of the q of x, this will be the sum from 1 to n of xi of q of ai. Just as what we had before, the expectation on the p of y, this was the supremum over e. We just typically don't write that p up there, but I mean, nothing prevents us from doing it. And then we just have on the x simple, and then the expectation of a simple guy on the p would be very similar to above, except we're putting a different measure in here.
What is the capital N?
It's,
That the sum is some.
to be simple, it means that you are a finite sum, right?
Oh, I see.
So this n here is not fixed, but it's some finite n. Right, so as what it means is that when you see the expectation, when we have multiple meshes, we're interested in expectations under these different meshes. And we need to have notation that indicates what measure we're integrating with respect to. Like you could have an example, right? There could be an example where you say x is standard normal, mean 0, variance 1, but this is on the p. Then you could have another measure, x is standard normal with mean 1, not standard normal, so it has mean 1, variance 1 on the q. And then, so here when I compute the expectation on the p of x, I will get 0, whereas when I compute the expectation here on the q, then it will be 1. And I could be interested here in knowing if this is the structure that I want, what's my radical derivative? Okay. Had this been a course where we'd have written exams, this could have been a wonderful exam question. Please tell me what is the radical derivative in such a model here. Any guesses?
Do we? I have a question. Do we? Wasn't there this fit condition we had to? Do we have to check the absolutely continuous condition
Yeah.
for Q and
But
P first?
if I can create a radical derivative, I am absolutely continuous, right?
Okay, so we're assuming that's true because you're asking what is this
Yeah.
direct.
So we could have created, I could have said, what about if I would put P, Q, what else could we put in here? R, N, maybe I could have a 0 and then a 2. So I do something else here. What about this one? So now I can ask, is there a dq to p, dr dp? I guess what if you go back to the original one, what we had just seen is that this expectation here can be calculated as an expectation on the P of X, and then you multiply down with the Q to P. And so you know that the expectation of X on the P is 0, but what is the expectation? And then you know when you multiply onto the radical derivative, you're going to get the 1 now. So what is this guy here? Alice, did I make you more confused or less confused about this EQ? Okay, so try to think about this, guys. Next time you can play with it again. Try to think about what is this the Q to P. Figure out what it is. Okay, it's time to go get some dinner. I just want to remind everybody that we have office hours again tomorrow morning. And if you haven't signed up for a slot, most of you have, so this is awesome. If you haven't signed up for a slot for your all exam, please do so. Office hours tomorrow morning, and then if not, I'll see you next week. Okay, good night.
Good night.